you have a lattice, what's the inside and what's the outside? The idea behind the original Hyperganic development was just to represent space. In the 1990s, there was an innovation in engineering called parametric design, where you defined the dimensions of your part in relation to other dimensions as a function.
What is high design and what is Hyperganic core?
Hyperganic core, writing software, algorithmic software to solve the design problems. And high design is a simplified, more accessible version of, underneath high design, it's Hyperganic core. Internally at Hyperganic is a unified workflow where the representation is consistent throughout. One of the challenges with the current generation of AI is it's not very good with numbers and it's not always reliable. There has been a lot of rapid advance in software development is the integration of very sophisticated artificial intelligence.
Thank you so much for being on the show today.
It's my pleasure. Thank you for having me.
I would like to understand your career path, going from software development, ending up at Hyperganic. So how was that for you, and why did you decide to end up working in engineering?
Well, that's a very interesting question. So I have been involved in software development for almost my whole life. So I sold my first commercial software when I was 14 years old. I've been developing software and managing software development and working on product management, software products, and helping other people with their software challenges in a consultancy role, basically my whole life. I have been working in CTO or director of technology level roles since 1998. In startups, I love working in startups. I've been working, the dynamism and the daily challenges that come with it. I really enjoy that. So this has basically been my career, is working to help companies develop their product ideas and bring them to market and help build teams that are able to deliver commercial software. So how did I become involved in Hyperganic? And how does that relate to my, interest in engineering? It's a bit of a coincidence. So I was initially contacted through a friend of a friend from the new management. Hyperganic had gone through a change of management. And they were looking for somebody who had sort of my background because they were trying to bring a commercial product to market. And that was originally the capacity in which I was approached. But I've had a lifelong interest in engineering and design on the side, starting from in middle school. I was taking courses in drafting and industrial design and shop class. That was a thing, metal shop and wood shop. Mm-hmm. And as the computer-aided design industry and product category evolved as a thing, because it wasn't when I was in middle school, I was very much involved with that, but never professionally. And when 3D printing became popularized through the rep-wrap style of filament printers, I got some of those for home and was using them as a hobby. When I was, whenever I had a project, like for example, I had an apartment that our family bought, and it was completely empty, brand new building, and it needed to be decorated. And so I bought CAD software and worked out exactly how all the flow through should go and everything. So I've always been very interested in designing things with software, but I've never done it professionally until I joined Hyperganic. And so joining Hyperganic has allowed me to combine these two interests into one. And I have been absolutely enjoying every bit of it. I've learned so much, and I'm working with some of the best people in the industry and challenge and working on some of the most interesting challenges in the industry. And so here I am, quite happy and very excited about where we're going as a company and with the products we're producing.
Really nice. I would like to understand. It sounds so simple when you say it, Michael, like combining software development and engineering, but what is actually the difficult part of it? Like, how do you make something so complex, like let's say sophisticated shape in engineering design, and write it as a piece of software? Like, what are some of the difficult bits that you've encountered that you encounter in software development when you work on an engineering task or problem? Because it sounds simple when you say it, but it's actually very tricky, I can imagine.
Well, so this is this gets into the challenges that we faced with additive manufacturing. The traditional sort of CAD software, CAD engineering software is fairly much. It's mature and it's based on technology, the hardware and the software technology of the late 1980s, early 1990s, and it wasn't that difficult of a challenge. In fact, one of when I was in middle school, one of the first pieces of software I wrote was a little flight simulator. And it's interesting that the mathematics that goes into creating three-dimensional games, which is what I was interested in at the time, is exactly the mathematics that you find being used in CAD packages today. There are a bit more complexities. So, for example, traditional CAD packages have focused on surface representations. So curved shapes are represented by a mathematical concept called NURBS,
Hmm.
non-uniform rational B-splines. This is an acronym for that, which is it's just math. I mean, it's somewhat complex math, but it is math. And then what they do is, you have your shape represented in NURBS, and then it turns it into a bunch of triangles, and it goes through your GPU. And then when you look at it in the screen, you have your GPU is taking these triangles and stacking them up and figuring out where they should be rendered. This is all technology that was well understood, and there were books written about it. Like I said, in the 80s and 90s, and I read those books. It's math. It all comes down to math, and then it's just a matter of writing the code to do the math. Where it gets challenging and interesting is when you are uh, trying to solve an engineering problem, and how do you want the software to help you do that? So one of the things that is commonly used in CAD programs is constraints. You say that this part has to be next to this part, or this line has to be perpendicular to that line. And
Hmm.
then you build up these constraints, and that helps you solve your problem. Because when you're doing, even back before there were computers, if you're doing drafting, you had to specify your dimensions. You say, well, this part is measured from here to here, and then this part is measured from here to here. And this diameter is, well, obviously diameters are just diameters, but the center of the circle, well, where do you put the center of the circle? It's in relation to something else. So it's always about these
Hmm.
relationships and these measurements and building those up to solve a problem. Again, it's math. Constraint solvers are a well-studied problem, and you understand the math, and then you write the software to do it. Then you get into the user interaction, which is a challenge completely independent from engineering and manufacturing, just to make a user interface that is easy to use. I don't know if anybody listening used the old style two-dimensional AutoCAD back in the 1980s, but usability was not a focus of that particular piece of
Mm.
software. And even though it was an industry standard.
Yeah. I'm wondering, you're solving this incredibly complex problems in Hyperganic. I'm wondering, from your perspective, Michael, do you feel that because you have innovation happening in software and innovation happening in hardware development on the engineering side, do you feel that software has to catch up to hardware or vice versa? So what's happening faster and what's the more difficult scenario?
So this is an interesting, and this is what makes working in Hyperganic so interesting, because we are at the intersection of uh, advances in additive manufacturing and advances in software.
Mm-hmm.
And they complement each other very well. So Hyperganic has been used and has had success being used in additive manufacturing because additive manufacturing allows you, it frees you from the constraints of traditional subtractive manufacturing. So with the traditional process of lathes, mills, drills, you start with a block of material and you take off parts from the outside. So you're always working from the outside in. You're taking off parts
Mm-hmm.
from the outside. Whereas with additive, you're building up parts by slices, usually. And that allows you to have structures internally. And it turns out that the traditional ways that traditional packages have represented objects, as I said earlier about surfaces, they're surface representations. And these are very well suited if you always have an outside and an inside and they're clearly delineated. But with additive, you are able to create shapes, lattice structures, TPMS structures, triply periodic minimal surfaces like gyroids. People might be familiar with gyroid fills if you're doing additive manufacturing. These are shapes that fill a space, but there's no clearly defined inside or outside. If you have a lattice, uh, what's the inside and what's the outside? If anybody's had the opportunity to climb up the Eiffel Tower, when you're inside the Eiffel Tower, you're not really inside. It's always, it's like this structure of connected beams, and there's a boundary. But the inside, what is the inside of the Eiffel Tower? Is it space? Is it iron? Where does it end? And CAD packages, traditional CAD packages, struggle to represent and manipulate highly complex space filling structures where there's no clearly defined inside and outside. Hyperganic, the idea behind the original Hyperganic development was just to represent space. Instead of representing the surface, you would represent space with something called voxels. So you would have a grid of cubes stacked up, like little tiny sugar cubes all stacked up. And then you would represent your shape that way. And it turns out this is a very, very close fit to how additive manufacturing works. So if you have a filament printer, you have a print head and it goes and it puts a little blob of polymer. If you have a powder printer, whether it's a metal printer or a polymer powder printer, you have a layer of powder and then you have a little laser and it puts a spot in it and it melts specific spots in space. And then you go up level by level. If you have a resin printer, you have you have a surface and then you have little beams of light and it turns on and turns off the polymerization of the resin at each individual spot. So the way that these manufacturing methods work, all of these additive manufacturing methods work, is there's a representation of a space that's filled up with material, dot by dot, location by location. So the challenges that traditional manufacturing software, CAD software, have, because there's an assumption with those tools of an inside and an outside, and it's at a very, very deep level of how the primitives for representation are designed. It's difficult for them to do this. And this is actually one of the challenges that we have with Hyperganic software is a lot of people, they say, well, okay, we love your software, we like the shapes you make, but we also want to import it into our CAD tool. And then when people do import it into their CAD tool, often the file sizes are too big, or it requires too much memory for the way that it's representing it, and it crashes. And then once they get it in, they're not able to manipulate it the way that it works with a traditional one, because there's no clear inside and outside. And the way that you traditionally manipulate your designs in a traditional CAD tool is you change where the surface is, but there's no surface. So this is an interesting area of development, because to be able to take full advantage of the capabilities of the potential of additive manufacturing, where you can precisely locate every single piece of material in your part, irrespective of where it is in relation to the outside, you need a tool that helps you unlock that potential. And so that's where Hyperganic has had a lot of success, is in those types of applications.
Yeah. Would you, everything that you've now described, Michael, would you summarize this as algorithmic engineering? Because you talked about the traditional approach, and what is the new approach, and what is algorithmic engineering in that regard?
Okay, so algorithmic engineering. So what I've talked about up to this point is about the internal representation, that basically the starting assumption of the design tool. And then algorithmic engineering is something that you build on top of that. In traditional engineering, going back thousands of years, I mean, as from the time that people started, building stone arches and designing, the geometric relations and analyzing static loads. The way that engineering has worked is you draw what you want to build, and you put some dimensions on it. In the 1990s, there was an innovation in engineering called parametric design, where you defined the dimensions of your part in relation to other dimensions as a function. So you say, well, let's say you have a building near an architect, and you don't want to put in all the windows. And you say, well, what we're going to do is we're going to put a window every 2 meters. And then if you expand your building, it fills in all the windows for you. If you contract your building, it takes out the windows. If you're doing some kind of, if you're designing a crane, you say, well, this is how thick the base needs to be, and this is how thick the tip needs to be. And as you make it longer, it fills in all the dimensions as a function. And if you make it shorter, it fills in all the dimensions. So parametric design was a big revolution for engineering. It was the first time in, 1,000 years that engineers were able to make changes to the design and not have to go and update every little dimension and respecify it, because it was defined as formulas. So these are parameters. Algorithmic engineering is sort of the next level beyond parametric design, where you define your problem in the form of a algorithmic solution to the problem. So an example of this might be trees. Just to give you an example from nature. So trees, why are trees tall? Well, trees are tall because they're competing for sunlight, and and also they need to be, if they go up to compete with sunlight, then they also need to be resistant to wind forces. So there is kind of an algorithm where a tree will grow up if it has plenty of light, it will grow, short and wide, and if there's not much light, it will grow tall and skinny, and then when it gets light, it will branch out, and then they'll get more leaves, and the leaves will orient themselves to the sun to get the maximum sunlight, get the maximum respiration, and it figures out at each stage where to grow and where not to grow based on simple rules that are applied. So it's not simply a parameter, it's reacting to the local conditions.
Mm-hmm.
And that's what algorithmic engineering is about, is you have a global objective that you're trying to solve with varying conditions. And in actual engineering, it can be things like you want to minimize the weight of your part, but maximize its rigidity in certain directions. So this is something called lightweighting. And so you have a global objective, but decisions need to be made locally. So if you're making something like a very lightweight motorcycle chassis, you will have parts of the chassis that are under greater stress and experience greater strain. And so you maybe need more material there. And then you have other parts where they're experiencing less. And this is something that you can derive from simulation, where the stress concentrations are. And then you achieve your global objective by establishing rules of how do you adapt to the local conditions, how do you adapt the part to the local conditions to get the global solution. And that's really probably the essence of algorithmic engineering, is defining your problem as a set of rules that if you follow these steps iteratively, that's the definition of an algorithm, is an iterative step of rules that are followed from input to output. You can get a design solution that achieves a global objective that would be almost impossible if you were doing it, manually or by trial and error. Because that's the alternative to algorithmic engineering, is manual engineering, where you simply state this is the dimension or this is the relationship between these dimensions if it's parametric. And then does it work or not? Well, you can either build it and see if it works, or you can simulate it, or you can rely on your experience and judgment and training. But it's not usually optimal unless there's already some established rule, like an arch needs to be this shape to be optimal. And then you say, okay, well, then my arch is this shape. But for anything more complex than something like an arch, you want to define the rules and the steps to follow to get the final output, the final shape, and the final material distribution and the relationship between the different parts to get your global optimum.
Yeah, very well explained, Michael. I like that. There's a lot of people in the market that work on the same type of problem, I would say, not parametric, but more like on the algorithmic engineering side of things. Who will win the race? Is it the one who figures out the quickest way to solve this problem? Is it the one that figures out the way to have this code that is the most generalizable one? Or what is it that you do at Hyperganic very, very well that serves your customer in every possible scenario or for different use cases? Is it speed? Is it applicability? What is it at the end of the day that makes you stand out?
So I don't really think that it's going to be a case where there's going to be like one winner and everyone else will be losers. I think that
Hmm.
there will be different ecological niches that will be filled. So, for example, we have a very comfortable ecological niche that is, we don't have any competitors for really, of embedded algorithmic design. So if somebody already has a package that does some sort of CAD like um, production, or it's part of an end to end design workflow, and they need some sophisticated algorithmic engineering bit in the middle, we work with those companies to put our software as a plugin to theirs. So it's
Hmm.
a component, a pluggable component. There are other companies that are focused much more on just a pure play design workflow. So, a tool for engineers to do design in the same way that you have existing CAD packages. And basically, it is you put in your specification, you get your design out, and then you have to figure out what to do with it downstream. And there are other players that they're packages that plug into existing uh, design tools. So, for example, the Grasshopper ecosystem, you can find very interesting tools that people have made building on Grasshopper. Uh, Many free, some commercial. So there's different ways of realizing the value of algorithmic design, algorithmic engineering, and different players will be stronger in different areas. One of the areas where I am most excited on our roadmap, because of our heritage as being a volumetric tool, we have been working with simulation techniques, finite cell method and lattice Boltzmann, that also complement the volumetric representation that we have built Hyperganic on, so that you do not need to change representation. In a traditional engineering workflow, you'll have your CAD, and it's a surface representation, and then you export your surface representation and you turn it into a mesh. If you're doing finite element analysis, it'll be like a quad mesh or a hex mesh, a tet mesh or a hex mesh, some volumetric meshing, and this is a very error prone and fragile process. Sometimes it needs many iterations. And then you export that into your simulation tool, because your simulation tool requires a mesh. It doesn't know what to do with NURBS. And then you get your simulation results out, and your simulation results are going to be values against whatever the mesh is. But then how do you convert the values that you have in the mesh to your original CAD? You have to do that by hand. It's a very labor intensive workflow that requires specialist skills, because the underlying representation isn't consistent. Whereas what we have been working on this past year internally at Hyperganic is a unified workflow where the representation is consistent throughout. So you take for example, if you're going to find a light weighting solution for a bracket, for example. So you have the bracket that's represented as a volume in space. You put that into the simulation, which simulates it as a volume in space. You get your simulation results back as a volume in space, which you can then directly apply those fields that come out of the simulation to your algorithmic design, and then the same loop happens internally without changing representations. This is something that you can only really do if you're starting from a foundation of a representation, a design representation, and a simulation configuration and the results that are all basically consistently volumetric. And nobody else has that ability right now. If you look at other players that are in the algorithmic design space that have simulation integration, you still have to change representations.
Hmm.
And so this is an area that I'm excited about solving this problem, because if we can solve that problem, it doesn't just have applications to additive manufacturing. It has applications to engineering generally, because anybody who is using simulation to optimize a part, no matter how the part is manufactured, if it has any complexity whatsoever, they have this challenge of import, export, remap, translate, and we get a lot of feedback that engineers really, this is the least favorite part of their job, and we have an
Hmm.
opportunity to fix that for engineering generally, not just additive.
That's really, really cool. Can you maybe differentiate what is high design and what is hypergenic core? Because I think when people browse your website, it's not quite clear what the differentiation is. Maybe you could quickly define what is high design and what is hypergenic core.
Yeah, that's a very good question. So Hyperganic historically was focused on a product strategy that involved end users writing software, writing C# code to solve their problems.
Hmm.
And this approach really restricted who was able to take advantage of Hyperganic. So a lot of the solutions that were built on Hyperganic core were built with the assistance of Hyperganic engineers. And what we wanted to do is, unleash the latent value in what we had built and make it accessible to a much broader audience. That basically presenting them a tool that they could use without having to spend a lot of time learning how to use it. They could solve simple problems quickly, and that's hyperganic. That's high design. So this is a web-based SaaS product that anybody with a web browser can start using in a couple minutes, and it doesn't currently expose the full capabilities of Hyperganic Core, because Hyperganic Core is only limited by effectively your imagination, your creativity, your ability to write software. But it does have a lot of the commonly used, commonly requested functionalities, and that's what high design is. It's democratizing uh, complex geometric operations for you know people involved in additive predominantly, who are designers,
Hmm.
or maybe they're engineers, but they're not specialists. And so we want to make it something that more and more people can use and get more value from. We've also currently we have in beta integrated simulation, so you can do linear elastic stress strain analysis of your parts. And just go into a different tab, set up your boundary conditions, how much force you want, and what your what direction the force is applied, and it will run a simulation and give you your results back. This is sort of a placeholder for the where the development roadmap is going, as I just described, about having integrated design, simulate, and optimize. Uh, so yeah, that's really the key difference. So we still do a lot of work with uh, parties that have challenging engineering problems, and we work with them using Hyperganic core and writing software, algorithmic software to solve the design problems. And high design is a sort of a simplified, more accessible version of underneath high design is Hyperganic core. I mean, it is
Hmm.
all of the software in high design. It's just a web UI on top of Hyperganic core. So on the back end, when you connect to high design on the back end, it's running exactly Hyperganic core. But we've put a user interface and selected useful geometric operations and
Got it.
simulation.
Got it. That makes sense. You talked about the different milestones, Mike, which is we had this in the 1990s, the parametric design era, I would say, or the major
Mm-hmm.
milestone that we had algorithmic engineering built on top of that. If you
Mm-hmm.
look into the future, Michael, of course, everybody talks about AI, but where do you see the future heading, especially for Hyperganic in the next 5 to 10 years? Like, what is the vision of you guys?
For AI, yeah, that's a very interesting question. We've looked at AI quite a bit, and we've identified certain areas where we can get immediate value, and we have identified areas where we are watching developments in artificial intelligence. So, in fact, our director of engineering is giving a talk on exactly this topic in Stuttgart, I think, right now. It is an active area. So one of the challenges with the current generation of AI is it's not very good with numbers and it's not always reliable.
Hmm.
So you'll have heard of hallucinations that the large language models have a tendency to hallucinate. If you ask them for a fact and that fact doesn't exist, they will make up a fact,
Yeah.
or they will confuse different facts and put them together. And it's not a significant obstacle when there's like a human in the loop looking and say, well, that doesn't make sense, or you can check up on it. And if it's low frequency that this happens, that's not, it's an acceptable issue. People are very, very happy using things like, Chat GPT and Anthropic's Claude, or, Twitter has Grok, and, Google has their AI. People use it; they get value from it, and the value is growing every day. But the thing is you always have to check the work. When you're doing engineering as a discipline in terms of what your objectives are and what your requirements are for engineering, it requires a higher level of precision. And AI at this point in time is not really good at spatial relationships and hard constraints. So it
Hmm.
doesn't understand numbers very well, and it doesn't understand spatial relationships very well. And that sort of makes it not really a very well qualified engineer. Where we have seen uh, immediate value for AI is in the acceleration of the simulation and optimization steps. So it turns out that the exact mechanisms that are used to train these language models are these mechanisms, the mathematics and the code and using the GPUs to accelerate this, and creating what's called a latent space representation of the world. This actually maps very well to engineering problems. So with a language model, the first thing that it does is it converts the text input, the prompt, into a vector of tokens, and each token itself is a vector. So effectively, you're creating a tensor, which is an engineering representation of multiple dimensions that are related to each other. So if you have a parametric design, you can take those parameters and you can dump them into a neural model. You can run some simulations and you can get some simulation results, and you can train an AI model the relationship between the parameters of your design and the simulation results. And this is very important because simulations, doing accurate simulations, is extremely compute intensive. Some kinds of fluid dynamics analyses, the simulations can run for weeks or in some cases months. It is, and even for standard, the type of simulations that engineers will run in the normal course, it's hours or days. So if you can shortcut that and create a trained model, a surrogate model, it's called, that has internalized the world model. So it can say, well, if you put these parameters in, what that happens downstream is you get these results. And this is sort of teaching the world to a neural model for a very small world, which is within this design space. If you have these inputs, you get these outputs. And it's very useful for that. We've already used this on some projects with good results, and it's very promising. And this is something that we're working on developing as part of our integrated design, simulate, optimize development roadmap.
Really interesting. Nice. As we have a lot of young engineers and professionals listening to this podcast, Michael, I would like to know from you, what are some of the key skills engineers will need to have, especially if we look into the future, for people who want to adopt this kind of algorithmic thinking, I would say, maybe the skill set of becoming an algorithmic thinker or a good engineer? Like, what key skills do they need in the future? Is it more like they need to become generalists or more specialists, or do we need a mix of both? How do you see that personally?
So I think the most important thing, and this isn't just, for this point in time, I think just generally, as as you understand the role of an engineer, design thinking is important. And I think what will happen as more and more of the routine aspects of engineering become automated or assisted through AI, the design thinking, understanding the constraints and objectives of the problem and thinking about it creatively and coming up with innovative solutions, elegant solutions. There's going to be more and more of a premium on that as more and more of the rote engineering gets automated away. I think that's the most important thing. And the next most important thing is the ability to understand the engineering problem in terms of rules and objectives, because this training of AI models to optimize, as I just discussed, in order for that to work, you need to have a parametric design. So you need to be able to define your design space. So if you're doing a bracket, like what are the interesting dimensions or parameters of a bracket? Like, well, how wide it is, how long it is, how many connection holes it has, how thick the material is. These are all parameters. So being able to think about the design in terms of what are the essential parameters of my design, and then being able to create a design around those parameters. And then also in terms of what does good look like quantitatively, says you're going to be asking the AI and the simulation software to optimize your design to create the best design. Well, what is best? How do you measure that? I mean, a common example in lightweighting is, well, you have a certain strength or rigidity target, but you want to remove unnecessary material. So how do you measure that? How do you quantify what good is, and how do you quantify better? So these are two skills. Normally, when you start off engineering, I mean, traditionally, it's like, well, okay, you have to like play around with parts and get some sense of, some spatial awareness, and then you just go start drawing it, right? It's like, well, I would need a bracket. It goes like this, goes like that, and you just draw it. It doesn't. You're not required to take a step back and understand in an abstract way what the full design space might be and how you define a better point in that design space, in that entire design space, and how do you find a worse point in that design space. If you can specify quantitatively the rules of better or worse and what the inputs are to the design, then you can automate the rest. And that's really the key thing going forward, is being able to understand the problem a step away from like just going and immediately drawing a solution, but actually say, well, yeah, this is a bracket. You look at it, you say that's a bracket, but how do you define the space of brackets? And that's something that I think perhaps most engineers don't really get a lot of practice. I'm like, well, define the entire universe of brackets parametrically. What does that look like? And then how do you define good brackets or versus bad brackets for a particular application? What's good? What's bad for a bracket?
Mm-hmm. Yeah.
And then that gets into like materials and then material simulation. And there's a whole bunch of other stuff that goes with that.
Yeah. How do you personally would advise people to practice critical thinking, especially when it comes to software development and or engineering? Because you've mentioned a couple of major skill sets that people would need to have, like design thinking, for example. But how do you practice it? Because I feel now with the age of large language models, especially students start to use it more as a substitute for their own thinking process. They're going to give it code or whatever, and they say, well, think for me. I'm going to lean back and wait for the results. And even if you hallucinate, I'm going to just take it as the single source of truth, whatever the output might be. So how do we practice critical thinking,
Well,
especially as software
that's
developers?
a very, very good question. And so, as I mentioned at the beginning, my career has been software development. And after you've done, software development for enough years, you have sort of a big picture understanding of how to approach a new problem. And what we've seen, where there has been a lot of rapid advance, particularly just in the last few months in software development, is the integration of very sophisticated artificial intelligence, such as the Claude Sonnet 3.5 or the O1 model that OpenAI just released.
Mm-hmm.
They are really good at writing software if given very correct instructions. And what we're seeing in the industry is senior experienced software developers and architects are able to leverage this ability very, very effectively because they have the experience of specifying and designing the solution. And traditionally, then their instructions would have been farmed off to junior developers to implement, and then the work would be checked in a code review. And senior software developers like, well, I can replace 10 junior developers just with Sonnet or O1. And this is I don't have the answer for it, but I know people joining the software development world today, they're graduating from university and they're looking for work. And it's already difficult to get a job, but getting a job where everybody's going, well, like, why would I hire somebody fresh out of university who doesn't know how to code when I can, pay $20 a month for some AI tool that's going to be a better coder?
Yeah.
So then to your question, well, how do you develop those skills if you don't get a chance to develop those skills? So we're creating this like gap, and it's going to be the same thing in engineering soon, I expect, where more and more of the routine stuff is automated. And then like, well, you can't get in at an entry level job because a computer's doing that. But in order to actually, get to the productive level, you need to work your way up the ladder. But
Yeah.
at this point in time, that ladder, and people haven't even started building that ladder. Like, how do we train people to be good, effective designers and get that experience so that they can then themselves leverage the ability of the artificial intelligence? It's a good question. I don't have the answer. It's a new question because 6 months ago, it wasn't like this.
That's evolving pretty quickly. Last question for you, Michael, then we can wrap it up, is how can people learn more about Hyperganic and your work you do with or at the interface between engineering and software development?
So where can we learn more about? So we have if you just go to hyperganic.com, we have case studies. We have our design tool. You can try High Design. It's a 30-day free trial if you're curious about what's there. And High Design today is it's the beginning of the roadmap. We released the commercial launch was only in July, so it's been not even 2 months old as a product, and we're continuing to improve on it. But if you want to see what's there now, there's a 30-day free trial. I welcome people to try it. We have, as I said, information on our site. You can browse around. And if you have any specific, particular, interesting, challenging engineering problem, be in touch, because that is a big business that we do, is helping people with their engineering problems. Everything from heat exchangers to 3D printed body parts. So we're actually working with bioprinting as well as more common customization, insoles and helmets and things like that. So take a look. If you have questions, be in touch.
Definitely. Michael Robinson, thank you so much. It was a pleasure talking to you.
It was a pleasure as well. Thank you very much for having me.